In previous scenarios, Livingston Medical Services has been trying various techniques in order to forecast medical transportation. Now it's time to try, in this scenario, simple exponential smoothing. Let's look. Livingston Medical Services is now considering simple exponential smoothing. Oh wait, that's this particular formula right here for forecasting future transportation demand. Livingston wishes to test alpha 0.05 and alpha 0.65. Oh, okay, important point. We're going to test a forecasting technique in this scenario. Actually, we're going to test two forecasting techniques. We're going to have to conduct two tests because two different alpha levels have been proposed for the simple exponential smoothing formula. Oh, all right, anyway. Using the same past data as listed in scenario 4A, right? We've been working on this before, and assuming in the case of both alpha values that the first month, October, begins with a perfectly accurate forecast, how does these applications perform? Oh, and you might be thinking, what's that business about a perfectly accurate forecast? What? Okay. In simple exponential smoothing, if you take a look at that formula, you see that your forecast for a certain month depends on what you had forecast the month before. Oh, so in order to simulate the use of simple exponential smoothing, because that's basically what we're going to do, we're going to simulate its use over these past couple of months, you have to start with the first month, but in the first month you need the forecast from the month before, and it's just a strange sort of space that you get into in working these problems on paper. That's a very common assumption. Just to get started, assume in the first month that the forecast was perfectly accurate. Then start using the technique. Oh, okay, now wait a minute. That means that we actually have a considerable amount of setup to do here, because if you have this note frame, it says using the past data from scenario 4A, the past data isn't actually pre-printed on the note frame, so we had better get that all set up. All right, we've got space to work here. You can see that. I'm going to draw some lines where my work will come out pretty crooked. The first month it had just mentioned was October. I'm just drawing a line. October, November, December, January, February, March, April, I want to keep these straight, May, and June. The past data was October through June of some previous time period. Okay, now what actually was the past data? I have that in my notes. Let's load that in next. Okay, the first month was October. And the actual was 10,230 transports. The next month, November, but you knew that, the actual number of transports was 12,004. The next month, December, actual was 10,990. The next month, January, the actual for January was 12,480. Then comes February. The actual was 11,568. Then comes March. Squeeze the whole month in there. Okay, the actual 13,244. So things are picking up for medical transportation in March. Then April, maybe I can squeeze the whole month in. April. The actual for April, 15,560. So picking up some more. Then comes May, nice and short month. 16034. So medical transportation continues to rise. Then June, wow, and then June, the actual was 2340, 23,400. So that was a big month for medical transportation, apparently. Now remember, this is just the data that we're working with. It isn't something that we determined. Now, what we were asked to do was to test the use of simple exponential smoothing. How good would it have been over these past months if we'd been using it with an alpha of 0.05 and an alpha of 0.65? We have to do them one at a time, so the particular note frame that I'm working with, you can see it's pre-printed at the top here. What's this space going to be? Simple exponential smoothing with an alpha of 0.05. Right, so that's what we'll work with here. Now, next, we determine what the forecasts would be. We determined what the forecasts would be to get started. That was that strange statement that in the first month, October, begins with a perfectly accurate forecast. Yes, we're just going to assume that what actually happened in October is what we happen to have said would happen. I can just fill that in. I was told to assume that. I was told to assume that, so it's not until November that we actually start using the forecasting tool, because we say, okay, what would the forecast have been for November? And I'm looking over here at the formula. My forecast for November would have been, okay, my forecast for the period before, so that's my forecast for October. My forecast for October was 10,230. We were just remarking that, right? Plus alpha, okay, we're doing 0.05 here, times what actually happened in October. 10,230 was the actual. No, wait a minute. And then the forecast was the same thing, because we were told to assume that, which means that's 0, which means you don't add anything, which means yes, your forecast for November is also 10,230. Now, you might think that that looks a little weird, but you can already see what the logic of simple exponential smoothing is. Simple exponential smoothing says, what's your forecast for next month? Take your forecast for last month, your old forecast, and add to it some percentage of by how much it was wrong. That's what the actual last month minus the forecast last month is. That's your error. Oh, well, because of our beginning assumption, in October, our forecast that month wasn't wrong. So simple exponential smoothing is saying, essentially, algebraically, oh, it was perfect last month. Then let's use it again. 10,230. Okay, it's not until the next month that we start to see some changes. Okay, that was the scratch work, for instance, for November. What about for December? Okay, what would the forecast be for December? Forecast for December. Well, it would be the forecast for November, the previous forecast. The forecast for November was that part right there. Plus the same old alpha times by how much it was wrong. Well, that was what actually happened in November minus what we had forecast would happen in November. Okay, so I did the arithmetic and I get, rounding 10,319. That's the result of that scratch work right there. Okay, so then that's my forecast for December. I'm just going to continue on. I did these calculations for each of the months. What would the forecast then be for January? Well, it would be the forecast for December, that's the 10,319, plus 0.05 times 10,990, what actually happened in December, minus 10,319, what we had forecast, or 10,352. Likewise, the forecast for February, you look back at the actual and the forecast for January, and you determined that the forecast for February would be 10,459. Gets adjusted up a little bit. Then in March, you say, okay, well in February I had forecast that, plus 0.05 times this minus that, and I get 10,514. Then for April, I say, okay, the forecast was that, minus 0.05 times this minus that. I get 10,651 as the forecast for April. The forecast for May, 10,896. And then the forecast for June, 11,153. All right, now what we have done is we have pretended like we were using simple exponential smoothing over these past couple months. The past couple months have already happened. That's why we have the actuals. Why are we doing this? Because like in the other scenarios, we're assessing if maybe this would be a better way to forecast in the future. And in order to do that, it asked us, what was the question here? How does either of the applications perform? How is this right here performing? We need to calculate some performance measures. Oh, all right. Now, the simplest of those performance measures, let me choose a contrasting ink color here. The simplest of those performance measures is simply to look at the errors. Now, error is actual minus forecast, and we could calculate that. Actually, we have two columns of data. We could calculate the error in each one of the months starting from October and then going all the way through June. I mean, that would be logical. This particular scenario, we're actually doing this because we want to compare our work to some earlier scenarios where we were using different techniques. And in those earlier scenarios, they didn't work with October through June. They only worked with January through June. I have this little note written to myself. And then they calculated the performance measures over January through June. And if we want to compare this to that earlier work, okay, then it would be logical here to only calculate the error measures over January through June. I'm just explaining that's why you're going to see me doing that. Oh, okay. You could do them for each of the months, but I'm going to drop in here at January. And I say, all right, now see it says error. What was the error in January? Error is actual minus forecast. So it's this column minus that column. The error in January was 2,128. Actual minus forecast, the error in February was 1,109. Actual minus forecast, the error in March was 2,730, excuse me. The actual minus forecast for April reveals an error of 4909. In May, 5138. And in June, 12247. Ooh, we were like way off in June. 23,000 some odd minus 11,000 some odd. The error is bigger than the original forecast. But never mind. Now, we're trying to assess this technique, and one assumes compare it to other techniques. One way to do that, one of the simplest performance measures, is to just average these together. That's the mean error, just averaging these together. I did that. I get, I'm rounding here, 4,710. Is that good or bad? Well, it's probably not good, but it's hard to say just looking at that number by itself. We do have some other techniques in previous scenarios to compare it to. At any rate, we do wish we saw 0, obviously, although even if we did see 0 in the case of mean error, that doesn't necessarily mean it was very accurate. All right, now, because it's not real reliable that way, another error measure is mean squared error. Oh, okay, mean squared error. You take each of the errors and you square them, then that's what you average? Right, that's why there's this other column. Well, let's take a look at that. That means I want to take each one of these numbers and square them, then average those up. Now, if I take this number and I square it, I get a very large number, 4527256. Okay, if I take 1,109, or this number, and I square it, I get 1230654. Okay, these are running in the millions. Or this number and square it, we're still in the millions, 7452249. Or this number, 4,909, square it, I get 24,102,079. Oh, no, wait. And before I complete that column, we should, a little note. Because maybe you're not just copying these down, maybe you're actually tracking along with me. And you took 4,909, you put it in your calculator and said times 4,909, right? Because we're squaring it. And you're looking at the display on your calculator and it looks slightly different than that number that I just copied down. You're going, wait a minute, I'm getting a little bit different numbers than you are. Yeah, that's called numerical instability. Don't worry about it. And you say, well, wait a minute. I mean, I know how to square a number, 4,909 times 4,909. How come I'm looking at a slightly different number? Because I didn't actually do each one of these computations separately on a calculator. Hopefully you won't have to do anything else like that on, say, an exam, any problem this large. No, actually what I did is I typed these numbers into a spreadsheet. I typed these numbers into a spreadsheet. We are writing them down by hand so that we can have this little tour and talk about how you might do this if you don't have a spreadsheet handy. A spreadsheet stores decimal places. You'll notice that I'm rounding here, just giving you whole numbers because that's good enough for the purpose of our tour. These numbers aren't coming out perfectly round. The spreadsheet is quietly storing all of the decimal places, and when I ask it to square a certain number, it's squaring the exact number, not the rounded version, and that's why what I'm reporting to you is slightly different in some cases than from what you're actually looking at if you punch the first number in as a round number into your calculator and square it. Okay? You say, well, it's different numbers, right? What's this supposed to mean? It means no matter how you do this, we're going to come out, you'll see this, by the end we're going to come out with the same conclusion, and that's what matters. Anyway, let's finish this column, because when you take this number, especially in a spreadsheet, and you square it, you get a very large number, 26,398,196. And then when you take this number, 12,247, and you square it, it explodes. 149,989,538. 104, almost 150 million. Oh, all right. Now, why did we do that? Because we wanted to know what the mean squared error was. That's where you just average these. I get 35,616,538. Is that a good number or a bad number? Well, it's almost assuredly not a particularly good number. It sure is awfully large. We do wish we saw 0. The one thing that we like is that if we see something close to 0, it does mean it was a perfectly accurate forecast. Mean squared error is reliable that way. Mean squared error is not all that great an accuracy measure, though for another reason, and you can definitely see it in this problem. We have one particularly bad error in June. That's the error of 12,000 some odd. When you take a large number, like you had one really bad error and you square it, it explodes. I rattled you off like nearly 153 million. When you average it, it kind of obscures what's going on. Do you notice that the mean squared error, 35 million, there was only 1 month that was actually larger than that number, but that does work out to be the mean. Okay, so mean squared error is a little squirrely that way. It exaggerates a few large errors, which is why we generally don't leave it there. We generally look at other error measures. Now, another error measure and a more popular error measure in practice is mean absolute deviation. To calculate mean absolute deviation, what you do is you go back to the errors and you average them, except you only average their absolute values. If you had any negative errors, you drop the sign. Oh, now, well, this is what's ironic with this particular problem, and also suspicious about this technique, is look, when you look at the errors, there aren't any negative signs. These are all positive errors, meaning that to fill out this particular worksheet, this is super easy. The only thing I need to do is copy that column over to this column. It turns out to be the same thing exactly. Let's see, 12,247. And obviously, when you average this, which is known as the MAD, the mean absolute deviation, you're going to get the same number that we got last time, 4,710. And that's because in this particular instance, we didn't have any negative errors. Oh, we said that mean error was a rather weak measure of accuracy, because when you average errors together, they can wipe each other out, you know, if you have positive and negative. It's a lousy measure of accuracy for that reason, but it's a good measure of bias. The fact that we didn't have any negative errors here across all these months of forecasting is indicating that the one thing that's already emerging is like not being that great about this particular technique in this particular setting is that it is strongly biased. All those positive errors mean that it's consistently forecasting too low. Okay, and that's basically no good. Anyway, we're not done with our assessment, because one other way that we can assess, and we can practice this, a forecast, is its mean absolute percent error. Now, to do that, we first want to, and you can see that one last column right here, we first want to calculate the percent absolute error. Now, whoa, wait a minute, what is percent error? I can squeeze that in here. Percent error, a little note to self, is just the regular error divided by the actual. It gives you a sense of scale. Percent absolute error is just that, except if it's got a negative sign, you drop it, and in this case, we were just remarking you sure don't have to worry about that. Okay, so for instance, our first percent error that we would put here for January, what we would want to do is take the absolute error, you know, that's that number right there, and divide it by, we have to go January, what was the actual, 12,480? That goes right here, and it works out to about 17%. 2,128 divided by the 12,480 is an error of about 17%. Okay, now we just need to do that for the other months. Oh, so we would say 1,109 divided by the original 11,568. I get an error of 9.6 for February, then an error of 20.6 for March, and then an error of 31.6% for April, and an error of 32% for May, and an error of, ooh, ouch, 52.3% for June, because it's 12,247 divided by the actual of 23,400. Average those together, that's known as the mean absolute percent error, and I get like about 27.2%. On average, you were off if you had been using this technique by about 27%. All right, now we were asked to comment on, okay, well, how are these techniques performing? We've just done the one, alpha equal 0.05. Those aren't great numbers. Now, they still right now, especially here, we're only looking at simple exponential smoothing, don't have a lot to compare them to. Okay, well, at least we could repeat this process for alpha equal 0.65. Maybe we will come out with some better measures. Well, let's take a look. First off, it's the same old thing. We got to get set up, because we have to do the whole thing over again. This is essentially a different forecasting technique, highly related, but a different one that we're going to simulate over the same set of months: October, November, December, January, February, March. Oops, I need to keep these lines straight. April, May, and we can quit at June. Okay, and it's the same data. We're starting over again. So we start with October, and the actual is 10,230. We then go on to November, and that's 12,004, and then December, and that is 10,990, and then January, and that is 12,480, and then February, that is 11,568, and then March, let me squeeze in the whole word March, and the actual for March had been 13,244. And then April, the actual for April had been 15,560, and then May, 16,034, and then June. That was that big month for medical transportation. 23,400 is what actually had happened. Okay, now it's time to simulate the use of simple exponential smoothing. Except now we use an alpha of 0.65. Now, the beginning is the same. We make the same assumption because we just need to get started here, right? We make the same assumption of that the forecast is the same as the actual. Then in November, we're going to get that same business of the exact same number back again because because October tested perfectly accurate. We're not going to get any different answers here than last time until December. Because, for instance, in December, the forecast for November would be, the forecast for December, now I'm trying to change that to DEC. The forecast for December would be the forecast for November plus, remember it's 0.65 here, times what actually happened in November minus the forecast for November. Okay, so we are going to get from there, what did I get? I got 11,383. That would have been our forecast for December, 11,383. Then in January, if you say, okay, the forecast for December plus 0.65 times what actually happened in December minus the forecast for December, I get a forecast of 11,128 for January. And then a forecast of 12,007 for February. And then in March, you say, okay, the forecast for February minus 0.65 times this minus that. I get for March a forecast of 11,722. And then in April, a forecast of 12,711. And then in May, a forecast of 14,563. And then in June, you say, okay, the forecast for May, this 14,563 plus 0.65 times this, what actually happened in May, minus this, what I had forecast for May, I get a forecast in June of 15,519. So we have a different set of forecasts because we're using, in essence, a slightly different technique. Oh, all right. We're using a slightly different technique. Now it is time to calculate the errors. And we'll do the same thing. We'll start in January so that we can compare to older scenarios. We'll start in January by just saying actual minus forecast. I get an error in January this time around of 1,352. Then in February, actual minus forecast, I get an error of, now wait a minute, actual minus forecast, here the error is negative 439. And then in March, actual minus forecast, I get an error of 1,522. And then in April, actual minus forecast, an error of 2,849. In May, actual minus forecast, an error of 1,471. And then June, actual minus forecast, an error of 7,881. Okay, so we still have this great big error in June. All right, so that's the error. We could calculate at this point the mean error, right? I average these numbers together. I get 2,440 for the mean error here, which if you want to sneak a look at the last page is actually a lot smaller than last time. But anyway, let's just go ahead and do all of the measures. Let's go ahead and do all of the measures. We next want to square those errors. That will get us set up for mean squared error. So I take the 1,352 and I square it, and it's going to explode into a huge number, 1,829,026. I take this negative 439 and I square it, and I'm going to get back a positive number, 192,418. Take this number and square it, and I get 2317917 as the squared error for March. Then for April, take this number and square it. I get 8,116,031. Then take this number and square it for May, and I get 2,164,143. Take this number for June, 7,881, and square it, and it explodes. 62108,363. Okay, never mind any one of those numbers. What we wanted to know is what's their average. Mean squared error, I just average these together. I get 1,2,7,8,7,9,8,3, a mean squared error of over 12 million. Oh, all right. Now, other errors, other error measures. How about the mean absolute the mean absolute deviation? That we just take the errors and we drop any signs. Okay, this is mostly just copying. The only sign here there to drop the absolute value of a negative 439 is just 439. Everything else is straight copying. 1471 and 7881 for a mean absolute deviation of 2,586. Okay. And then finally, to get a sense of scale, just like we did last time, we could convert the errors into percent errors. Then we could take the absolute values. Let's see, if you take this 13,052 and you divide by what was the actual 12,480, you reveal that the percent error and the absolute percent error, for that matter, for January was about 10%. I get 10.8%. In February, that divided by the actual, I get an error of 3.8%, so not much of an error. In March, this number, 1,522, divided by the actual for March, I get 11.5%. Let's see, for April, that number divided by the actual turns out to be kind of hefty, 18.3%. In May, 1,471 divided by the actual for May backs it down to 9.2% error. But unfortunately, in June, if you take the 7,881, that was our absolute error and our error, and you divide it by 23,400, we are off by 33.7%. Mean absolute percent error is just averaging all of these. I get 14.5%. Okay, now these are 4 performance measure readings, and we were asked, well, how is these 2 techniques performing? And this is one thing that I can do, is this is 0.05 that we're looking at here. This is alpha equal 0.65. I notice that the mean error is smaller. I notice that the mean squared error is smaller. I notice that the mean absolute deviation is smaller, and I notice that the mean absolute percent is smaller. So in a certain sense, you could say, oh, alpha equal 0.65, the second one we did, it wins. It does win in terms of these performance measures. It is definitely better than alpha of 0.05. That doesn't mean, though, it was very good forecasting technique. I mean, we were just given an open-ended question to comment on its performance. Comment on its performance. Alpha equal 0.65 is better than 0.05. That's true. Okay. However, its performance measures are not good. Even with nothing to compare it to, I mean, these are still some pretty plump numbers. And we should note, had better measures from forecasting techniques discussed earlier. Because if you look back, you know, we're in scenario 4B right now. If you look back at some of the previous scenarios, why were we only assessing January through June? Because we wanted it to match some of the work that was done in the earlier scenarios for a fair comparison. That fair comparison shows that after all of this work, we really don't recommend simple exponential smoothing for this particular scenario.